喂，好，slide 27. So long time ago, we talked about the catalytic reaction. There are 7 steps for the catalytic reaction. And the step 1, 2, 6, 7 belongs to the mass transfer. Step 3, 4, 5 belongs to the reaction. Okay, so last time we have gone to the first step, external diffusion, right? So section 10.2.2.1, step 1, the diffusion from back to the external transport. So this diffusion is influenced by the size, by the diameter of catalyst, and also the rate of flow. So I think there is still one figure I have not talked about, right? At the slide 27, at the bottom side. So there is a figure. So when you see a figure, you have to find what is the y and the x-axis. So for y, that is overall rate. Overall rate. Overall rate is the total rate. You combine step 1 to 7, the whole reaction rate. So from step 1 to 7, the overall rate. So this one is not only for step 1, okay? But now we are talking about step 1. But in this figure, this is overall rate, okay? How about the x-axis? U over dp. U is the rate, flow rate for the, or you can call it fluid velocity. Okay, that is the flow rate for the liquid. And the dP is the diameter of catalyst or of particle catalyst. This P means particle, the catalyst particle. Okay. And then, how about the curve? We can divide the curve into 2 parts. So let's have a line here. So this curve actually can be separated by this kind of shade. And also, it's like a parallel line. Okay, so there are 2, you can separate it into 2 parts. And also you can see from this figure, in this part, if I define it as part 1 and part 2, for part 1, you can see from the figure, external diffusion is the slowest step, right? What is the meaning for slowest step? The slowest step means rate limiting or rate determining step, right? So the overall rate is determined by the slowest one. So in Chinese, Okay, so part 1, external diffusion. External diffusion is step 1. We're talking about now, right? External diffusion is the slowest step. Okay, so for this region, you can find the overall rate is proportional to U over dP. Let me write down more. Okay, so at a part 1, or portion 1, the overall rate is proportional to U over dP, right? And also you can use other expression. The overall rate means the external diffusion rate. They are the same thing because external diffusion is the rate limiting step here. So external diffusion rate is proportional to U over dP. Okay, so last time, you can see other sentences at this slide. We compare low velocity and the high velocity. So the diffusion rate is proportional to U, right? The faster your reactant or your fluid, the higher rate for diffusion. So this one, the flow rate for the reactant is proportional to the diffusion rate. Okay, and how about the dP? For dP, you can see the figures at slide 26. There are two sizes of the particle, so different sizes of the catalyst. There will be different thickness for the boundary layer. Okay, so dP, particle size or particle diameter, influence the boundary layer thickness. So the diffusion rate is inversely proportional to dP. Okay, so at part 1, this curve is like this because at part 1, overall rate is determined by external diffusion rate. Okay, and then at this region, part 2, when the particle becomes smaller or when the velocity becomes higher, we can go to this part, right? So at this part, the external diffusion will be faster. So it no longer be the rate limiting step. So part 2, external diffusion, or in the figure you can see that is external mass transfer. The same thing, okay? Is no longer the slowest step. So U over dP is has less influences on overall rate. Okay. That is the reason why in part 2 the curve is like this. Like this means with increasing U over dP, the value for overall rate is almost unchanged, right? Because at this region, the external diffusion is highly related to U and dP, right? Highly related to length. But at this region, external diffusion is no longer the slowest step, so it cannot influence the overall rate anymore. So please understand how to explain this figure. you have to understand how to explain this figure. So at the first, you have to find in y-axis, that is overall rate. It is overall rate. So if I change this one into external diffusion rate, if I change this one into external diffusion rate, this one could be like this, okay? If it is external diffusion rate, the step 1, external diffusion rate is always influenced by U and the dP. So the larger U over dP, the larger external diffusion rate. Okay. So that is very different. You have to find this one. What is the physical parameter in y-axis? Okay, can I go to the next? Next step, step 2, internal diffusion. Okay, so for the external diffusion is, this is step 1, right? External diffusion from the bulk, CAB, B is bulk. From the bulk solution to the surface. The target is A. A is the objective. Concentration A in bulk. Concentration A at the surface of catalyst. Surface of catalyst. So from here to here, step 1. So now, from the surface into the inner of catalyst, it is step 2. Okay. So we define the surface concentration as a CAS. We define the interior concentration of A as a CA. So at step 2, we only talk about CAS and the CA. We don't want to talk about CAB anymore because the CAB is for external diffusion. Okay, let's find some important terms at slide 28. Okay, we are now at slide 28. Consider the internal diffusion is the slowest step. So now at step 2, if this one is the slowest one, the first point, reactant A diffused from surface into the pellet interior. Okay. And after diffuse into the interior of pellet, the reactant diffuse into the interior of pellet, it react with catalyst. With catalyst deposit at a pole wall. So like this. If this is a pole, it is defined as pole wall. Simple definition, okay. So the reactant diffuse into the pellet or catalyst and react at the pole walls. So for this step, we only consider dP. We don't have to consider fluid velocity anymore because we are in the interior of the pellet. Okay, only at this part we consider the velocity of fluid, but inside interior For the interior or internal diffusion, we only consider dP. So here, dP is the only factor to influence the diffusion. So we can separate it into large dP or small dP, okay? So for large particle size, diffusion time, for large particle size, there is a long way to go. The path is long, so diffusion time will be larger than reaction time. Okay? Inversely, for small particle size, the diffusion time is smaller than reaction time. And the rate of reaction, I think that is part you have to write down something. The rate of reaction equals to Kr. Kr is a rate constant times Cs. But actually, it is better to have this one, CAS minus CA. However, when reactant A diffuse into the inner side and react with catalyst, Ca could be almost equal to 0. After reaction, right? Diffuse into the inner side, Ca could be almost equals to 0. So, or you can say CAS is much larger than Ca. So finally we got this one. However, the rate is proportional to the concentration difference. Right, concentration difference. So this is the standard form. However, CAS could be much larger than Ca, so the final form is this one. Okay, so the most important thing you have to memorize is that internal diffusion, the only factor to influence internal diffusion is particle size, dP. So again, we can see like a similar figure. Please go to slide 29. Okay, there is a figure. For figure A, you can see the particle like this, okay? The similar one. Figure A shows the CAS and the Ca, right? CAS should be larger than Ca. Your material can diffuse into the inner part. And let's see the figure B. You can see figure B, the y-axis is Kr. Actually, Kr is defined as overall rate constant. Cr is defined as overall rate constant. So, again, you can consider the y-axis as overall rate, the same as previous one. And how about the x? dP. Okay, at this part, the only factor to influence the diffusion is dP, is particle size. So at the x-axis, we only have dP. Okay, so again, we can separate this figure into two parts. The first part is almost a parallel line, and the second part decrease with increasing dP. Okay, we can see this part first. So again, part 1 and part 2. Part 2. Part 2 means the large, right? The large particle size. Okay? For large particle size, diffusion time is larger. Diffusion time is larger. So the internal diffusion is the slowest step. Right? So also we can call it rate limiting step. So at this step, the internal diffusion rate is almost equal to the overall rate. So you can compare this figure as the previous one. Very similar. Okay, so overall rate is similar to internal diffusion rate here. And you know the internal diffusion rate is inversely proportional to dP, okay? So the particle, if the particle is larger, the diffusion is smaller. The diffusion rate is smaller, so inversely proportional. So you can see part 2, right? With larger dP, the overall rate decreases. Okay, so the same for part 1. You know what's happened in part 1, right? So again, part 1, small dP, so small dP means the internal diffusion is faster, much faster, so it is no longer the rate limiting step. So small dP, internal diffusion is no longer the rate limiting step. So in the figure, you can see the figure use the other expression. If the diffusion step is no longer the rate limiting step, the other kind of step like surface reaction could be the slowest step. Okay, so from the figure you see this sentence, right? From the figure you see this one, but this one is also the same as this one, the same thing. So if you want to have a consistent expression for 2 figures, that is this one. So because internal diffusion is no longer the rate limiting step, so the overall rate is less influenced by dP. Okay, so you see the almost unchanged value, almost unchanged overall rate with increasing dP. Any question? So we have finished step 1 and 2. We have finished the diffusion. Actually, that is step 1, 2, 6, and 7, right? Because step 6 is internal diffusion. Step 7 is external diffusion. So we have finished the discussion for step 1, 2, 6, and 7. And the main part in this chapter is step 3, 4, and 5. So we have more discussion on these steps. So let's continue. Okay. Step 3, adsorption. Adsorption means when you diffuse into the inner side of catalyst, the reactant should adsorb on the surface of catalyst, right? So how about what is the adsorption? At this section, finally, we have to plot the adsorption isotherm. Okay, so what is adsorption isotherm? Isotherm means this one, right? So the temperature will not change. Temperature will not change. At the same temperature, we draw a plot. So this isotherm is the relation of pressure and concentration. Okay, so finally, we will have this one. And in different behavior mechanism, we will have different figures. So if you see the figure, you do the experiment, right? You do the experiment, and you have several data. You draw the isotherm. So when you observe the isotherm, you can know what is the behavior. So for the adsorption part. Okay, so let's start with a very simple chemical reaction. Okay, A is the reactant, always. A is the reactant. S is the active site. Okay, S is the active site of the catalyst. So for the adsorption process, adsorption step, reactant A and the active site combine to be A dot S. So for the attachment of A on S, we use this one. Okay, A dot S means A is attached. A is adsorbed on the active site. Okay, and then let's see some definition. Okay, the The first definition here is the total molar concentration of active site. Okay, CI, first definition. You can see the first one. CI, and also you can see the unit. It is better for you to understand the definition. So CI, the unit is mole per gram catalyst. So it is the active site concentration. Okay, per unit mass of catalyst. So actually here we use gram per gram catalyst. This is the first definition. Okay, so second one, CV. What is CV? Again, you put a unit here. Mole gram catalyst. CV, the second one. Okay, so what is CV? CV is the vacant. You know vacant? 空缺 vacant site concentration. CV, vacant site concentration, again per mass of catalyst. Some important information have right down here, right? I have already provided to you. So now we define the CI, CV, and the third one is assumption. Third one is assumption. It's assumption. So the assumption means in real world. Actually, in real world, this condition is less happened. 很少发生这些事情哈。But to have easier calculation, we have to assume something. So you see the third one. Assume the total concentration of active sites remains constant. So the assumption is no deactivation of catalyst. You know deactivation, right? You know deactivation. But in real world, the catalyst will deactive with time. Actually, it will deactive with time. But for easier calculation, we have to assume the active site remain the same. So the total active sites remain the same. 我们假设它不会失去活性，不然你没有办法固定一个活性位点的数量来计算。好，所以我们这边要假设这一颗催化剂上面的活性位点就是不会变，我们才能计算，不然我们无法估计它随着时间有多少的量会消失，对吧？但是实际上随着时间，它的活性位点会渐渐的变少。好。但我们没有办法这样算，因为每个 case 也不一样。所以第三个不是实际会发生，那我们要推估一些图的话，我们要来假设它不会失去活性。So the total active site remains the same, remains constant. You can see this sentence at your handout. The total concentration of active sites remain constant. Okay, so there are two definition and one assumption for this part. Okay. And what's more, still have some definition, you can see PI and the CIS, right? PI and the CIS. PI means the pressure of species I, you can see here. For gas, especially for gas, we use pressure. Pressure is better for gas, and concentration is better for liquid, right? So usually for gas kind of reactant, we use pressure. And how about this one? CIS, this is important, very important. What is CIS? CIS is the surface concentration of sites. What is this site? Occupied by species. Species could be reactant. Species could be reactant or product. Some species. Okay. So I could be A or B if the reactant is A, if the product is B, I can be A or B, right? So AS, CIS, if you replace I using A, CAS means the concentration of sites occupied by reactant A, AS, okay? And if you see the CBS means the concentration of site occupied by product B. Okay, so after defining these parameters, we have an important conclusion. I think you have to write down, right? The total, at the bottom side, the total concentration of sites or active sites. Okay, actually the site is active site. Sites means active sites. Okay, so let me just write sites after all. What is this one? CT. Okay. Total concentration of sites, we define it as CT. So it is like you can see a figure here. Assume these are the active sites. So assume there are 4 active sites on the catalyst. For this site, it may be occupied by A. For this site, it may be occupied by B, right? How about this 2? This 2 is called vacant, 空缺, vacant site. So what is the CT? Total concentration of sites could be vacant site concentration, and the site occupied by A also occupied by B. So please write down this one. It is important. Total concentration of sites. We will use this for every calculation process. Also, we call it as site balance. Okay, please go to the next one. Okay, the first 2 points is to explain the isotherm. Yeah, I think I have already explained this to you, right? So first one, slide 31. Okay, so that's 31. Adsorption data are frequently reported as adsorption isotherm. So frequently, we use adsorption isotherm to report the data. Second one, what is isotherm? Isotherm means at one temperature. At one temperature, okay. And we talk about the amount of gas or liquid, but it is the reactant. We talk about the amount of gas absorbed on the solid at a different pressure. Okay, so this plot is a matter for amount of gas versus pressure. As I told you before, right? P vs Ca, P vs Ca, the relation between them, that is isotherm. Okay, so now that is the main part. We have two models. So we will plot two kind of isotherm for two models. We want to understand the model for your experiment. Okay, that is the process. So I will show you two different isotherm by replacing, placing the two different models. So the first one, for example, if we talk about carbon monoxide, CO, okay, so the first one, if the adsorption is like a molecular, or you can call it as non-dissociated. It is typo, okay? 有个错字，你看它第一点 ，non-dissociated， 它应该是写成 ciared， 第一点是 ate， 可以吗？你把这个 non 分开 ，dissociated， it should be t. Please modify this one. Okay, so the first one is called molecular or non-dissociated adsorption. So that means this adsorption, let me finish this too, okay? This adsorption is to use CO. CO is together to adsorb on the surface. So second one, you can see the second one at the slide 32, okay? So at 32, atomic or dissociated adsorption。这跟讲义有点不一样，你可以写一致，好吧？ If you want to have consistent expression, you can modify the terms I give you. So that means the adsorption is separated C and O. Okay, the atom C and O separately adsorbed on the surface. So we have these two kind of models. Okay. Thank you. So now I want to introduce these two models. So let's go back to slide 31. Molecular adsorption. Okay. The reactant is CO carbon monoxide. So slide 31, molecular non-dissociated adsorption. CO is adsorbed as molecules CO, so the reaction is CO and the active site, right? Becomes CO adsorbed on active site. That is the chemical reaction. For example, there is an example shown at the bottom side. If the catalyst is nickel, okay, if the catalyst is nickel, you can see it's like CO and several nickel atoms becomes CO, the molecular CO adsorbed at a certain active site. Okay. So by using nickel as the catalyst, CO, the behavior, the model for CO, adsorption model for CO is like this, molecular adsorption. And the next slide, 32. Atomic adsorption, right? Atomic adsorption, so CO are separately adsorbed on the active site. So there should be two active sites, right? Because C and O separately adsorbed on the active site. CS, OS. So it is the case with iron as catalyst. Okay, so if CO is catalyzed by iron, C and O will separately adsorbed. Like one CO here, or one C here, or here. So that is the case with iron as catalyst. Okay, next. Let's go back to this case, molecular adsorption. So now I will derive the relation between concentration and the pressure. Okay, for this case, slide 33. For this case. So the purpose is to find the COS versus PCO, okay? The isotherm, adsorption, purpose. Please understand the purpose. So first one. So there are 3 points we have to understand for this case. Okay, so understand 3 points. The purpose is to draw the isotherm. First one, the rate of attachment of CO on the active site is proportional to the number of collisions the molecule make with the surface active site per second。我讲中文好，这个第一点告诉你呢，这个 CO 接在活性位点上的数量的速率的 rate 跟碰撞次数成正比，所以这是个重点，就是 CO 碰撞活性位置越多次，它越有可能接上去，好吗？所以第一点 rate of CO attachment is proportional to the number of collisions between CO and the active site per second. Okay, because it is a rate, so per second. Secondly, the collision rate is proportional to the partial pressure. 越多 CO 存在就会撞越多次。好，像我们就是看多少碰撞越多越容易接上去。第二点告诉你浓度越高，碰撞次数会越高。所以第二点，let's have a relation between pressure and the concentration. Okay, P equals to CRT. Because the purpose, finally we want the pressure, right? So you have to put a pressure term. We want the pressure term. So P equals to CRT. Second one. Third one. CO adsorbed only on vacant site and not on sites already occupied. 已经被占据的位置，它不会再上去，它只会接到空的地方。好，它只会接空的地方，被接就不会再接了，它只会接到空的地方。所以 the rate of attachment is proportional to the concentration of active sites. So that means rate of CO attachment is proportional to concentration of vacant site. Okay, so now you know two things. The rate of attachment of CO is proportional to pressure of CO and the vacant site concentration. Okay, so finally you can write down this at the bottom side. Finally, we have a conclusion. So A and the vacant site, right, becomes a vacant site. A attached, occupied on vacant site. We call it as attachment of CO. Okay, so rate of attachment of CO equals to, or we can say it is proportional. It is proportional to pressure and the vacant site concentration, right? But if you want to replace the proportion by the equal sign, you have to show the constant. Okay, so constant Ka, PCO, CV. So for this part, we talk about the attachment, not the adsorption. Okay, it is not it is not it is not a desorption. At this part, we talk about attachment of CO. Next, slide 34, we talk about detachment of CO. So, originally there is A occupied on the active site. How about the detachment? It could detach, right? Without reaction. Without reaction, it will detach. So now we talk about the detachment of CO. Okay? You can see the first sentence. The attachment of CO, the attachment of CO or A, I use A, but let us CO. The attachment of CO from surface is proportional to the concentration of sites occupied. So this one is proportional to COS, right? So the more sites occupied by CO, the detachment rate will be higher. Therefore, rate of detachment of CO is proportional to COS, or replace the proportional by using the equal sign, K minus A, okay? Rate constant, and the COS. So we have the equation for attachment and detachment. So at a single adsorption step, attachment and detachment could happen at the same time. So we have to sum up these two, so that it will be the rate of adsorption. Okay, so next. Next, net rate of adsorption. Okay, it should be attachment minus detachment, right? So rate of attachment minus rate of detachment. Therefore, the equation is like this. The net rate of adsorption, we use the RAD. Okay, this one is RAD, adsorption AD. So rate of adsorption equals to rate of attachment. We can copy this one, KA PCO CV, right? Minus rate of detachment layer, K minus A CCOS. And also we can combine these two terms. We can combine them by using single KA. Okay, single KA. Bring the constant outside. PCO CV minus. We use an equilibrium constant. Okay. As you may know, Ka is rate constant, the forward rate constant over reverse rate constant, Ka here.这应该写在3、4页正中间哦。但如果你写不下，再自己找位置，好吧？There are some explanation for rate constant, the absorption rate constant Ka and the desorption constant K minus A, and also equilibrium of the absorption constant K, capital Ka. Okay. At the bottom side of this slide, it is just the explanation for Ka, K minus A, and the equilibrium constant Ka, right? There are 3 points at the bottom side. So Ka means the absorption rate constant, K minus A means desorption constant, and the capital Ka means equilibrium of the absorption constant. Okay, and Ka is independent of temperature. Okay. K minus A is proportional to temperature. So, because capital Ka is Ka over K minus A, therefore it is proportional to the inversely proportional to temperature. Okay. So that's the relation of constant and the temperature. Ka is the constant for attachment. So attachment constant is independent of temperature. However, the detachment constant, if at a higher temperature, the detachment will be more serious at a higher temperature. So the detachment rate constant is proportional to the temperature. So if you want to talk about equilibrium of the absorption constant, it is equal to this one, right? Ka over K minus A. So this one independent, this one proportional to, so this one is inversely proportional to the temperature. So it will decrease exponentially with increasing temperature. Okay. There are still some spaces, I think, at the bottom side. So maybe it depends on you. You can write down this again or skip this one. So for this one, AS becomes AS. The absorption rate is Ka Pa Cv minus Cas Ka. Okay. It's just a general form. The general form. Okay, so do you still remember the purpose? No? The purpose is to draw the isotherm. Right, the purpose is to draw isotherm. So we need a equation. We need to draw a plot with some equation. So let's see here. Please see here. This is the equation, right? This is the equation. This is the equation. Right? And want to draw the isotherm. So what is the isotherm? What is the XY for isotherm? PCO, COS. Okay, that is the X and Y for isotherm. We will draw this later. Isotherm. So why I'm talking about this? Because we want the relation between PCO and the CCOS. So please check this one. Where is PCO? PCO here. CCOS here. What is the remainder? This is constant, right? Constant is okay. Constant. Constant. How about this one? CV. CV. We have no idea about CV. So now the next step is to find CV. Okay, so I don't suggest you to memorize everything, but you have to know the purpose. Right, the purpose is to draw the isotherm. So you want the relation between these two. So you have to examine, like this is the final equation we obtain, right? The final equation. So you have to examine where is these two parameters in the final equation, and how about the remaining parameters? So the remaining parameters can be any constant. Constant is okay, but this one is not constant. We have to solve this now. So if you remember, we have talked about site balance before. CV exists in the site balance equation. So please go to next slide, 35. 35, let's solve CV. Okay, we have to replace CV. So at slide 35, right, 35, CO is the only material adsorbed on the catalyst. So the site balance, the total concentration of sites equals to vacant site and the occupied site. Okay. And we only have CO, only one species CO adsorbed on the active site, so vacant COS. So this is the first one. Secondly, we want to talk about the condition at the equilibrium. It is very important because at equilibrium, the rate equals to 0. So we talk about equilibrium, at equilibrium, okay. At equilibrium, RD equals to 0, right? At equilibrium, the forward and the reverse reaction are almost the same. So RAD rate of adsorption equals to 0. Okay. If this one equals to 0, let's bring that one. Ka PCO CV I just copy the formula. Right? This one equals to 0. So, CCOS. Okay, why I do this? Because I want this is y, right? This is x. This is y, this is x. I want the function y equals to something. Okay, that is the purpose. You have to know the purpose. Don't just memorize. So if this one equals to 0, this one equals to 0, right? Because constant is not 0, this one equals to 0. So CCOS is, right? And then you can check if this one can be used to draw the plot. Not, right? Because CV, again, CV, so where is CV? CV here. Please use site balance to replace CV by using CT minus CCOS. Okay? Site balance. Almost done. Okay, let's check again. If you see this one, is that okay to draw the isotherm? We got the CCOS, right? CCOS is the y-axis for the plot. PCO is the x-axis for the plot. This one is constant. How about this one? Actually, CT is constant as well. CT is the total concentration of site. It is constant because the assumption. 我们假设活性位置不会变 so CT is a constant. CT can be appeared at the final equation. So that one is okay. So finally, we have to rearrange. You can do this by yourself, okay? Just rearrange. You got this one. You can try to do this by yourself. So that is the equation for the adsorption isotherm. So we can draw a plot later. So this form, okay, it is important. This form is called the Langmuir isotherm. This type. We have two models, right? We have two models. This is one of the models. So for this model, it's called the Langmuir isotherm. Any question? Before drawing the plot, let me review again. Okay, let me review again. First, you have to understand what is the purpose. The purpose is to draw an isotherm. So we have two models, molecular model and atomic models. This is the first model. So that is the molecular adsorption. So to draw the isotherm, we have to find the relation between concentration and the pressure. That is the purpose, concentration and the pressure. Okay, so we know the rate of attachment and the rate of detachment. We know these two different ways of reaction, and we sum up these two, we got the rate of adsorption. Okay, so at the first equation for the adsorption rate, there are still one concentration unknown. Which one? CV, right? We got a vacant site concentration in that equation. So we use site balance. So finally we use site balance to replace CV using CT and CCOS. So finally we got that equation. So that equation expresses the Wigner isotherm. Okay, so let's draw the plot. To draw the plot, first determine what is the y and the x axis. So it could be better if you have the unit. Okay. So let's see this one. It is a little bit complicated, right? Because that is y, but we have 2x here. Do you know how to simplify this one? To simplify this one, we have to talk about this part. Okay, so the first case at low PCO, okay? We divide the region into two parts. So first, at a low PCO. At a low PCO, we assume right? PCO is small. So if one is larger, much larger than KAPCO, the equation is simplified as this one, right? And compare the original equation. Okay? And I have mentioned the Ka and the Ct are constant. So that means concentration of COS is proportional to pressure of CO. Therefore, at a smaller region, we got like a linear, right? Linear one, linear, the small region. And be careful, you should transfer through the 0, 0. You should have the original point, right? You can see this one. 0, 0 is one of the point, right? 0, 0. So it is very important for the beginning point. So if you draw like this, this is wrong. Okay, this is wrong because you know 0, 0 is one of the point. So be careful at the beginning. Secondly, at a high PCO, Let me use other color. At a high PCO, 1 is much smaller. Okay, so we reduce the original formula into which one? Okay, so it is a constant. So at the larger PCO, it is almost unchanged. Okay, so this is the log-meal isotherm. So if you see this type, you will know the behavior. So you do experiment, you got the data, you draw this, and you will know which model is for your experiment. Any question? Oh, we still have one plot for this model. Yeah, we can finish. This is one kind of plot. Any question? Okay, we still have one more plot for this model. Please go to slide, next slide, 37. Okay, checking whether a model predicts the behavior of the experimental. So we need another plot. So here, begin from the original formula, this one. Okay, let's do one thing. Let's inverse the sequence, okay? So first, okay, inverse. Is that okay? Secondly, let's multiply PCO at both sides. Okay, multiply PCO at both sides. Finally, I separate them into two terms. Okay, so finally I got this one. What is the new plot? The new plot is to draw the PCO over CCOS versus PCO, okay? So you can compare that one and this one. So actually, this is Y, right? This is X. So the slope is 1 over CT, and this is the intercept. So you may gather this time, this line linear. And you can extend this one to gather this one. Okay, so this value equals to 1 over KACT, and the slope is 1 over CT. And this one is for molecular adsorption. Okay, so for molecular adsorption, you have linear relation of these two parameters. So on the other hand, if you do experiment and you get the data, try to draw this figure. If you find a linear relation, that means you put this parameter at the y-axis, this parameter at the x-axis. You got a linear relation. If you got a linear relation, that means your data conform to the linear single-site isotherm. Okay, so that is the purpose. You can just draw the figure. You can just plot your data. And you observe your figure, you can know which model is consistent to your experiment. Okay.